you've actually already looked at roses. You looked at roses with having one petal. So we have already looked at this format when r equals the a times the cosine of 1 theta, when n is 1. And if I jump ahead just for a moment, that's when we got these circles. When that n value is 1, you get one petal on your rose. Okay, I'm not sure why they call them roses. They end up looking more like, daisy, where you can pluck the petals off, but they're called roses. Now there's a couple things to remember, that depending on what your multiplier is inside the trig function, that's going to change your number of petals. But if the petals is odd, you will see distinctly that number of petals. If the petals are even, you're going to see twice as many petals. So you can see an example. Here is r equals 5 cosine of 3 theta. Okay, so this is an odd multiplier inside the trig function. That means I'm going to have 3 petals. Notice it is still symmetric with the x-axis. And then I have a multiplier out in front of 5. That's going to tell me how long each of my petals are going to be. So when I plug in 0 pi here into this function, so r equals 5 cosine of 3 times 0 pi. 3 times 0 is 0, so the cosine at 0 is 1. I get 5 times 1, which is why I see my first petal right here along the x-axis. Now you might be asking yourself, well, how do I get these other petals? Well, we can plug in our other values, like we did with the cardioid. I could start and rotate around to pi over 2. I can get r equals 5 times the cosine of 3 times pi over 2. Well, notice because of that multiplier of 3, I'm not evaluating at pi over 2, I'm evaluating at 3 pi over 2. Well, the cosine at 3 pi over 2 is still 0, so 5 times 0 gives me 0, which puts me back at that origin, that pole right in the middle. So how do I know where the other petals are? Well, I have to think about the impact of this 3 on the angle I'm plugging in there. So let's think about other values, maybe not at the directly on the axis. Maybe I plug in a value like pi over 3. Let's think about why I would want to do that. Well, because I have a little bit of number sense. And I have r equals 5 times the cosine of 3 times pi over 3. So the reason I'm plugging in pi over 3 is so the multiplier of 3 and the denominator of 3 cancel, and I get 5 times the cosine of pi. Well, the cosine of pi, I know that's negative 1. So I get a radius of negative 5. I plugged in pi over 3, and I got a radius of negative 5. Well, think about where that is. Pi over 3 would be in the first quadrant, but that negative radius sends me into the opposite quadrant, that third quadrant, giving me that petal right there. Okay, so let's do some exploring on Desmos with our roses. I'm going to click off our cardioids. Okay. And now I'm working with an A and an N value. So let's go to our roses down here. I'm gonna highlight cosine and sine. So just like I said, when n is 1, which it is right now, when n is 1, we just get these circles. Okay? Circle in the positive x direction, The green circle for sine is in the positive y direction. But what happens when, and I'm going to set my radius can stay at 2. Notice what happens as I change the multiplier out in front. When I change it to 2, let's maybe not look at both. Let's look at sine. When I change it to 2, I end up seeing 4 petals. That's because 2 is an even number. This is going to have to be a detail that you remember. If the multiplier inside with theta is even, you're going to see twice as many petals. With 3, now I only see 3 petals. Okay, a table of values can be really helpful for knowing where those petals are going to be. Just plugging in different values and creating a table of values. And we could look at that at another time. Okay, when I get to 4, I see 8 petals. When I get to 5, I only see 5 petals. And I think you get the point. And then if I want the petals to be longer, I just change the A value. If A gets bigger, the petals get bigger. It can be fun to make different shapes with these different types of functions on the polar curve. All right, and then lastly, the last thing I want to talk about is just going back. Make sure you understand these circles and how to get a line. Okay, there's 2 types of circles, or like I mentioned, it's really just a rose with 1 petal, or then you have a circle centered at the origin. Okay, centered at 0, 0, and you get that from just r equals 2. And then the other thing we can see is theta equals some angle of rotation, and that will form a line, meaning it doesn't matter what the radius is. The r can be -5, the r can be +5. As long as theta is pi over 3, you're going to be a point on this line. All right, just to wrap up, I know this has been a lengthy video. I'm hoping it's helpful. What you're going to need to be able to do this week is being able to look at a function and identify what kind of polar you're working with, okay? And you can always use Desmos as a check, right? So when I look at this function, I notice that there's nothing being added or subtracted to it. There's no constant. I have a scalar and I have the trig function. So that means I'm dealing with a rose. Now I need to think about where that rose would be. So the multiplier in front of theta is 1. So this is just a rose with 1 petal. So I'm going to have a circle. It's cosine. I'm going to have a circle from the origin. Oops, let me move that circle along the x-axis. And it's this petal, if I'm thinking about its petal, this petal goes out a length of 4. Okay, let's take another look at one below. You have 5 minus 2 sine of theta. Okay, now I have a constant. I'm going to label this my A and my B value. So 5 is A. My B value is going to be the 2. I'm going to deal with the negative with the fact that this is going to open down. So I've got to compare A and B. A is greater than B. And I do want to make a point. I'm ignoring the minus sign. The minus sign is telling me that this limestone is going to open down along the y-axis. Why the y-axis? Because I see that this is a sine function. Okay, so 5 minus 2 is 3. So that's going to be my innermost tip. So the point of my limestone is going to be at 3. This is going to open down. 5 plus 2 is 7, but since it's opening down, I'm going to be, that 7 is going to be down here. And then the sides of my limestone are going to be this A value, which is 5. So when I connect these dots, I end up with this crazy puffy marshmallow looking thing that I didn't do a very good job drawing. If you want to get a better idea of what that looks like, then make sure you plug that into Desmos. All right, let's just try a few more on here. So -7 sine of 10 theta. So this, I'm not even going to try to draw this. This is going to be a rose. This is going to be a rose because I have this multiplier in front of here, and it's going to have 20 petals. So this will be, I'm going to go ahead and do some typing. This will be a rose with 20 petals because that's an even number. And the length of each petal is going to be 7. It really is that negative is going to send the petals in an opposite direction, but it's not going to change that the length of the petal is 7. All right, let's do one more. I'm going to do this last problem right down here on the left side, 4 plus 7 sine of theta. So again, sine, this means this limacone, there is a constant out in front. This limacone is going to open along the positive sine axis. So my furthest tip's going to be up here. So 4 plus 7 is 11. So A plus B, that's going to be my furthest tip. That's 11. And then the A value is 4. So the sides of this limacone are going to go out to 4, where sine is at its midline will be 4. And then the innermost tip is going to be 4 minus 7. Well, that gets me a negative radius. Sine is usually at its minimum. Well, sine is at its minimum at 3 pi over 2. Well, when I plug in 3 pi over 2, I get a negative 1. So when I plug in 4 plus 7 times the sine at 3 pi over 2, when I evaluate the sine at 3 pi over 2, that becomes negative 1. So I'm really evaluating 4 plus negative 7, which is a negative 3. That's why I end up with a loop inside at negative 3. Because here's 3 pi over 2, but that negative radius means I have to go in the opposite direction. So this limacone is going to go up and out and over, and then inside. Get that loop. Oh, beautiful. And we'll look more in future weeks exactly the route these polar curves are taking and the order of their movement. That will be for a future lesson. So I hope you stuck with me. Go ahead and use Desmos as your guide. Use your teachers as a resources. Ask questions, communicate, and take care. Stay healthy and happy.